condition that the engine could see in flight. We tried to make it more severe than the engine would ever see while flying in service.
All that and more coming up next on Mega Machines.
Check out our next machine.
Next on Mega Machines, we're hitting the afterburners with a full-throttled machine that's powering the future of air travel. It's the GE90 115V jet engine.
That's what you're gonna work on.
This Jurassic-scaled engine, designed to power the world's largest aircraft, stretches 24 feet long, gapes 11 feet wide, and weighs a flight-defying 18,000 pounds. That's 9 tons.
Just in case you didn't know.
This jumbo jet will need $21 million to do it. And be sure to read the fine print, because the plane's not included. But spark this puppy up and put the thrusters on full, and you'll realize what you're paying for.
Currently, the GE90-115D is the most powerful aircraft engine in the world. And in January of this year, it set a new world record at 127,900 pounds thrust.
But notice how they're
Terry
testing
Craig
that.
and Shaker
A little bit of
Sharur
an
are two of the
asymmetric
hot shots
configuration
behind
they
this
have.
mother of all
It's the only way
motors.
you can really get
Their
full
creation
self-flight
is more than
testing.
twice as powerful. And oh yeah, twice the size of a standard 747 jet engine. In fact, mounted next to normal engines, it's so muscle-bound that it can blow away 400-pound chunks of concrete.
Entering the inlet now, as you can see, we have 22 forward swept fan blades. The unique shape of these blades is a result of GE's 3D aero design. The composite blade was first introduced on the GE90 engine. All the other engines typically have metal and titanium blades. These blades are mainly a composite body with a metal leading trailing edge, very durable.
The revolutionary blade design allows this monster motor to suck in and spit out nearly 2 tons of air a second at takeoff.
Remember, someone brought that up at a meeting. They said that's a great idea. Rev.
Some people suck at marketing.
Just to give you an idea, if you put this car, this van in front of this engine at takeoff thrust, it'll get sucked in.
It's powerful, yes, but is it reliable? Well, GE not only builds this beast, they also try to break it.
Of course, the biggest concern that's on our mind, most of all, is safety. A twin airplane or even a 4-engine airplane cannot afford to have an engine fail.
Actually, not true.
Each one of those engines
The
will go
design.
through a battery of testing.
That's okay.
Not only do we try to simulate any type of condition that the engine could see in flight, we try to make it more severe than the engine would ever see while flying in service.
First up, they try to stall it with 1,100 gallons, or 4.5 tons of water a minute. The equivalent of running this engine through a once-in-a-century rainstorm.
The water ingestion test is to simulate a big rainstorm. Obviously, this engine, the airplane has to fly in a rainstorm, so we pump this huge amount of water into the engine to demonstrate that the engine will not stall.
Then they try to smash it with hefty chunks of ice.
We do perform an ice slab ingestion test as part of our certification program, and that essentially simulates if ice were to build up on the inlet of the aircraft and break off and get ingested in the engine and would not cause any damage to the engine or any operability problems. It actually gets chopped up by the fan blades and goes right out the back.
Finally, they try to choke it with 3/4 of a ton of hail.
The hail ingestion test is a test rig that we have to simulate a hailstorm. We actually have several cannons that fire hail balls into the engine to assure again that there's no significant engine damage and will operate safely.
And the result? An engine that's earned its wings. And with an unheard of.
All right, so we'll stop it there. I want to kind of give you an idea of the sense of the scale, some of the stuff we're going to be talking about. But as you're seeing that test, keep in mind that there's a group of engineers that's designing the engine, and there's a whole group of engineers that's trying to break it, right? And personally, I'd rather be on that latter side. It's a fun job to do stuff like that. All right. So obviously, what we're going to be starting today is a new set on propulsion. But before we move on to propulsion, I want to finish up a couple of topics related to aerodynamics. And if you recall, we're talking about high lift in our last lecture. And I came across these in the wind tunnel, so I didn't mention this, so I thought I'd go ahead and bring them by. So these are the big ass fan blades. And so they're actually both big ass fan blades and big ass fan blades. Now this was the original one. And you can see here it has this little gurney flap on the back, which serves two purposes. One, which we already talked about, high lift, so increases the lift a little bit. What's the other purpose? Yeah, structural rigidity. Basically, how they manufacture these things is to keep them relatively inexpensive, is they just extrude it. It's all extruded aluminum beams coming out. So that way, regardless of how big your fan is going to be, they can chop them off at 6 feet, 12 feet, 30 feet, whatever that's going to be, and they use the exact same blade for all of that. Now, a little bit about ceiling fans, right? Because this is what these are set up for. All ceiling fan designs, for the most part, are pretty bad from an aerodynamic standpoint. This one, not an exception for that. Primarily because you have this straight blade that goes all the way out. And this is going to be an important part of the whole propulsion discussion as we move forward. This is nothing more than an airfoil, and there is our wing, just extruded out. When we start flying this in a kind of level and steady flight configuration, that means we're pretty much having the same conditions across our entire wing. So it's seeing the same angle of attack. When you start rotating this, however, at the same time that you have flow coming in, now what that does is it gives you a changing angle of attack as you go out from the axis of rotation out towards the tip. So what you'll notice on most propellers is how you counteract that effect is you twist the blade. You provide washout throughout the entire blade length from the hub all the way out to the tip. So you start off with a really high angle attack near the hub, where your radius, your arm is very, very small, but your rotation rate is exactly the same because it's rotating as a solid body, and then you lower the angle attack all the way to get out towards the tip. Now, most ceiling fan blades, just for cost, just do the same thing as done here, right? Just extrude all the way. Now, what they found was, well, this was still pretty suboptimal, because this piece here, which was added for rigidity, does give you a little bit higher lift, but it also gives you what? Higher drag. So that means higher torque as you're rotating the blade around, and that's how big your motor is going to be. So what we help them do is essentially design a better blade, and this is what they do now. So it gives them, this is, I believe we ended up with an EPLA blade off of this, but just a little custom modifications to it to meet their kind of range of Reynolds numbers and rotation rates that they're going to be seeing. But you'll notice that it has a much higher camber associated with it. It's still pretty rigid based upon this curvature. So it achieves the same kind of structural goal requirement for this. You'll notice there are a couple of stiffeners in here. So that way you can go get by with a thinner skin, meaning lower material, lower weight, lower overall cost, but a much, much higher aerodynamic performance as part of this. Now, what can you not do with this that you can do with, say, your home ceiling fan? Reverse it. Reverse it, right, which you should never do. Ceiling fan should always blow down. Why do they have a reversal function on there? So people, when they go to Lowe's or Home Depot, they go, oh, this one's reversible. Although you should never reverse it. It sounds better when you say, oh, it's reversible. Just because you have reversible sweatpants doesn't mean you should actually wear them. And anyway, so you can take a look at these after class if you want to. All right, so to kind of finish up this discussion, I wanted to mention a couple of things really quickly. This is where we ended up in our aerodynamics lecture. We're going to start off directly with this, because this is going to drive everything on our propulsion side. We can't begin to size our aircraft engine requirements until we know what these aerodynamic performance parameters start to look like. And that leads us back towards the drag polar as well, and coming up with things such as best speed. So we're going to have our basic drag polar, and as we've already talked about, we can use our drag polar to determine where our best operating condition for maximum LVD is going to be at. And what we're going to see is as we strap different type of propulsion systems on board our aircraft, that's going to dictate what actually happens at this point. For example, it could be a best range point, or it could be a best endurance point, depending upon the propulsion system that we have on board our aircraft. Now, for this particular case, we can go back to that initial comparison that we looked at all the way at the beginning of the semester, where we had our Boeing B-47, our Avro Vulcan. Remember, basically two different ways to solve the same problem. Very different overall configurations, our flying wing and then our tube and wing geometry, but they ended up with kind of very similar types of performance parameters in their overall max takeoff weight, even though their wing areas were really, really different. However, that Avro Vulcan had a slightly better LVD ratio, but you end up with very different drag polars, which are going to drive you to very different operating points and condition. Even though these numbers are very similar to one another, due to the fact that you end up having a different drag point, lower drag point for your Avro Vulcan, even though your lift to drag ratios are going to be about the same, you end up having a different operating point. And if something like cruise speed, if you're cruising at a particular velocity, is of particular importance for you, that can dictate where you're going to lie within that particular range. And what other operating parameters are going to be important for your aircraft, such as, well, what should your cruise lift coefficient be? Very different for your Vulcan as opposed to your B-47. Now, this drives us to a little bit in terms of asking questions about maximum lift to drag ratio, because that's going to be a critical design parameter for us. So we can go back to this drag polar, and I don't want to go through the derivation here. Most of this is pretty straightforward, where we say, yeah, I want to find my maximum lift to drag ratio at a given lift coefficient. How do we do that? We take the derivative again, set it equal to 0, and then just do a lot of algebra on it to solve for that point. And that's all we're doing here in this derivation. This is just here so you can look at the details of that. But the end result is it allows us to find that lift to drag ratio point, or sorry, I should say that maximum lift to drag ratio point, as a function of our aerodynamic parameters. Primarily our span, our wetted area, total wetted area of the aircraft, and then the drag coefficient of that. You can actually write this in terms of the skin friction drag as well as an option. And so notice that this doesn't take into account what the aircraft looks like, but it does take into account some very critical parameters that you can pull out for each one of these and determine what that lift to drag ratio is going to be, and then where that operating point is at. And that's going to drive a lot of the stuff we're going to talk about from here on out in terms of how we integrate all these components into the aircraft. Now, over time, what we've been able to do is if you look at something like a tube and wing configuration, say, oh, nothing's really changed since the B-47, right? Kind of the same general wing configuration, same fuselage configuration, tail sit on the back. What you will note is in the details, and going back historically to our first commercial jet engines, or first 737s roll off the line, these are much better now than the 747 on 777. You'll notice that we have been able to improve that overall zero lift drag coefficient. And that has a really important impact on what our propulsion requirements are gonna be in terms of the size and performance of the engines. You also notice something a little subtle here, starting off with a DC-9, which is essentially the parent aircraft of our MD-80. So we'll go out and take a look at the MD-80 later this semester. If you walk on board the MD-80 and look at the type cert that is right on the door, you know, you can see that on every aircraft when you get on. It doesn't say MD-80, it says DC-9. And that was because it was a derivative of the DC-9. It was a lot easier to get it through FAA approval that way, by keeping it labeled as the DC-9 for FAA purposes and then marketing as a new aircraft. But you'll notice that the engines have really changed in terms of their overall diameter and scale. Now, the gas turbine portion of the engine is actually about the same. It's changed as the fan, and that's one of the details we're going to get into when we start talking about the gas turbine piece. Now, I want to finish off with this, with another back of the envelope in terms of calculating lift to drag ratio. So some very basic things on your aircraft. Obviously, you want to make lift to drag ratio as high as possible. So how do you do that? You give yourself a high span. That's not always going to be doable if you have other things going on in your aircraft. For example, wave drag, that's compressible drag. You want to make sure that your stall is going to be acceptable. You start getting high span, you're going to be more susceptible to things such as spin. So large cantilever beam. So your wing is going to get heavier if you start increasing your aspect ratio, even if you keep wing area the same. So how do you deal with that? Well, you come back and look at this basic equation that derived, and there are different ways that you can essentially formulate this to give you a better idea of how to deal with those different things competing in your aircraft. Notice span, skid friction coefficient, weighted area. So if you want to try to maximize this, don't just worry about span, you can also focus on these other drivers as well to try to get you to that same maximum drag ratio. So as an example of that, you know, the Tortoise is a really good drag coefficient, but they lack a fundamental piece, which is a really good propulsion system. You know, you throw a jet engine on these suckers and they just take off. Zoom back to that. Okay. Now, that leads us to our final piece, which is this right here. We have this curve. That's our aerodynamic curve. Thrust required, power required. What we need is that other curve, and that's going to be the part that we'll start talking about next. So moving straight into our propulsion slides. Actually, let's start from here. I'll forget before I start talking about these. A little bit of historical perspective, and we'll throw in some things here. Anyone recognize this aircraft? Yeah, so the ME-262 was the first operational jet fighter. So during World War II, we had 3 groups working on jet aircraft. In the later stages of the war, we had the Germans, we had the British, we had the Americans. Both the British and the Americans were able to develop jet aircraft during the war and test fly them, but not operationally. So the Germans would put this into service, late 1944, early 1945, right as the Allies were closing in. Notice, so this is a little worse for wear. Just pretend it's been out flying around and got shot by a P-51, so it's missing the needle here. But you'll notice that these are using what we'll call classic turbojets, so there's no fan on it. But we're going to be really focusing on the fan for a lot of our aircraft designs. But very similar to the configuration that you might see on the 737 a couple of decades later. And it was interesting performance. You'll notice the rest of the aircraft, it's a little bit of sweep in the wings. The Germans actually understood compressible wave drag better than anyone else at that time, primarily through a lot of wind tunnel testing. But other than that, the aircraft looks very similar to what other aircraft you'd see in the air at the time. However, most of the pilots that came up against this, the Allies, I had no idea what this was that was flying at them, from over the skies of Germany. And it flew about 100 miles an hour faster than the fastest Allied aircraft. So that's a substantial difference there, about 20%. Now, just 2 decades later, we have this. Of course, everyone knows as the SR-71. So you can get an idea of how rapidly jet engine technology advanced just in 2 decades to go from this thing flying about 500 miles an hour, right? So, Mach 0.7 or so, to this thing flying Mach 3, really, really fast, right? Much higher altitudes. And it was a combination gas turbine at lower altitudes, scramjet at, or should I say ramjet at higher altitudes. Be very careful, not a scramjet, it's a ramjet. But in this case, very small amount of time, very, very rapid advances in terms of your capabilities. Now, how you look at an aircraft, as we already know, depends greatly on what perspective you're looking at it from. So everything that we've done up to this point has kind of led us to think about aircraft designs that kind of look like this. We want to maximize lift-to-drag ratio, trying to get the best aerodynamic performance possible. Let's really shoot that lift-to-drag ratio up. Now we're going to look at this from a completely different perspective. So as propulsion engineers, we're going to look at an aircraft like this. All we care about is the engine. We just want to make the engine as big as possible. We don't care about aerodynamic. You need to go faster? Just put a bigger engine on it. That's fine. You can work it out. You need to carry more fuel? Fine. Put a bigger engine on it. Okay? So this is going to be a very different way of looking at things. And then we'll come back at the end of the day and say, okay, now we've got to meet somewhere in the middle. We can't have this. We can't have this. We've got to have a combination of the two. Now, what this boils down to, one of the reasons that we're obviously very fixated on fixed-wing flight is the efficiency aspect of it. And you can relate this directly back to thrust requirements. If you look at each of these, right, our fixed-wing flight, for example, we have in level and steady flight, lift, drag, thrust, weight. Lift has to be equal to weight, thrust has to be equal to drag. And we know from our equation, thrust is equal to weight divided by lift-to-drag ratio. Anything over 1, right, is essentially free aerodynamic forces for us, because it's going to lower our overall required thrust for that given weight. Now, if we go into a vertical takeoff mode, we have our weight and our lift. And our lift in this case is now powered lift. So it's coming directly from our propulsion forces that we have on board our engine. So thrust is equal to weight. That's it. And it's a much simpler equation, but we lose this elegance of this aerodynamic effect that reduces our overall thrust requirements, assuming our weights are equal. So given the same weight for both these aircraft, this requires a larger power plant than this one does. Now, that doesn't include the actual power effects. This is just assuming your propulsive thrust that's being generated. When you start looking in terms of the overall power requirements, we see that grows nonlinearly, going all the way back to the scaling arguments that we made at the beginning of the semester. So it's not a simple linear relationship, and it's primarily to deal with the velocity, but also how the propulsion systems are being generated for the aircraft. So we can go back to that same lift-to-drag ratio impacts that we talked about earlier and say, hey, here's my maximum lift-to-drag ratio. Here's a relationship between that span and that weighted area for that maximum lift-to-drag ratio equation that we just derived. And you can go all the way out to really, really high lift-to-drag ratios, which means you can minimize your overall propulsion requirements of your aircraft. So as the aerodynamicists on your team, this is what you should be fighting for, right? Say, hey,